I'm excited. I'm going to talk about something I've wanted to for years. The removal of adhesives, this is just a piece of tegaderm, from skin. There were two factors that kind of pushed this into the do it now category. I was so impressed with Petra Davidson and the ASET Skin Safety Task Force, their work on lesioning of skin. I knew that there was a little bit more to this to add to that story. And secondly, COVID has me climbing the walls from being inside all day, and I wanted to do something fun. So the topic is removing adhesives from skin. It's actually some complex physics. What are the variables, and what should we consider when we remove our electrodes or adhesives like this tape from skin? This is a demonstration of forces at different angles. There's an engineering term called force vectors. Let's just think of it as forces at different angles. I'm going to lift a 20-pound dumbbell. The bottom rope is, or the bottom scale is showing the force in the bottom rope, which is 20 pounds. And then we've got two ropes up top that are splitting that weight. So they should each have what? 10 pounds, right? The red marker shows the actual force. As we go out, what happens? That force in each one increases, and back in should be back towards 10, and back out, and the force goes up. Why is that? That's the question. This is a simple animated demonstration that most of you should be able to relate to from having to lift things. Person 1 is lifting two equal weight buckets as far out to the side as possible. Person 2 is lifting identical buckets halfway out to the side, and person 3 is holding identical buckets down to their sides, at least hanging as freely as the body and the way allows. Who has the hardest job? It is intuitive that person 1 has the hardest job, followed by person 2, with person 3 having the easiest job. It's just harder to hold something further out to the side. It feels heavier, right? How about doing tug of war? Do tug of warriors stand upright when they start pulling against their opposition? Of course not. If they did, when they pull, they would fall over forward because they have a poor base of support. They naturally lean back. These are intuitive things. We all instinctively know them, but these demonstrate some of the most basic physics of forces. Moving down to holding only a single bucket is even more demonstrative. Do you stand perfectly upright holding a single bucket? No, you don't stand straight up, you lean. Our experiences with lifting stuff tell us that, right? The bucket, of course, is creating a force pointing straight down. The person is providing an equal and opposite force. The force is pointing straight up. But there's a horizontal force that the body is generating to counteract a horizontal force the bucket is generating because of hanging off to the side of the body. One could say that this horizontal force is a biomechanically wasted force the body is having to generate due to the positioning of the bucket off to the side of the body. What if we had the same person move the bucket to the front of the body holding it with both hands? The horizontal force is no longer there in the side-to-side direction, is it? The only forces are the weight of the bucket straight down and the equal and opposite force generated by our muscles lifting straight up. The need for the body to generate the biomechanically wasted force side to side is no longer there. Of course, if the person turned sideways, yes, we would see that the bucket is being held out front of the body and a horizontal force would now be present in that plane. But hey, right now, for this discussion, we're only talking about the forward-facing view we see. In order to understand these forces more fully, it's helpful to return to the study of triangles, trigonometry, where we can use known angles and dimensions to find other values. No need to dig into a painful level yet. A demonstration of two hanging weights will help. We can easily see that both vertical ropes will have 1,000 pounds of force. But what about the two angled ropes at the top on the right? These two ropes are clearly splitting the forces, but will each rope have 500 pounds or some other value? The math will tell us that if the angle between the ropes is 60 degrees as shown, each rope will actually have 577 pounds of force. The vertical component would be 500 pounds for each side, facing straight up to provide the force needed to lift the 1,000-pound weight, with a horizontal component of 288 pounds for each side. So how were these numbers calculated? Hey, turn away if math makes your head hurt. We can assume this angle is 30 degrees, exactly half of 60 degrees. We can also assume this angle is 30 degrees as well, since the two white lines are parallel. We know this vertical force component is 500 pounds, right? The force needed to support 1/2 of the 1,000 pounds. It is the adjacent leg of the triangle. Here is the hypotenuse leg of the triangle. Here is the opposite leg of the triangle. So let's find that hypotenuse leg. We could start with the cosine trig function where we know both the adjacent and the angle values. Solving for the hypotenuse, we get the adjacent divided by the cosine of the angle, which is 500 pounds divided by 0.866, which yields 577 pounds. So we know this value, the tension in the rope, is 577 pounds. To find the adjacent leg value, we could start with the tangent trig equation since we know both the adjacent and angle values. Solving for the opposite leg, we get the tangent of the angle multiplied times the adjacent, which is 0.5774 times 500 pounds, which yields 288 pounds. So we know this value, the horizontal component, is 288 pounds. The same physics and mathematics which yield these numbers apply to our situation of the person holding the bucket. Holding the bucket with both hands in front generates no horizontal force component. Holding the bucket down to the side generates a small horizontal force component. Holding the bucket far out to the side generates a larger horizontal force component and will almost always be accompanied by a larger lean. The body has to try hard to generate that large force. Note here that the vertical bucket force was the same in every case. These horizontal forces shown were only present because of the way the person was holding the bucket. The same physics apply to adhesive items we remove from skin. Theoretically, if we pull a piece of tape with a reverse angle, like is shown here, the pull force includes a vertical force component as well as a horizontal force component. Theoretically, if we pull a piece of tape straight upward, the pull force includes a vertical force component, but zero horizontal force component. And theoretically, if we pull a piece of tape with a forward angle, the pull force includes a vertical force component as well as a horizontal force component. We need to study a bit more about what these forces do in removing the tape. Let's put a piece of tape exactly on top of the skin where we can see it from the side and zoom in on it. A 90-degree reference line that is perpendicular with the skin surface will help us in our demonstration. If we pull the tape with this reverse angle, we will establish this horizontal force component and this vertical force component. It is obvious that both the vertical and horizontal force components tend to remove the tape. If we pull the tape with this forward angle, we will also establish a horizontal and vertical force component as highlighted here. We can see this vertical force component clearly tends to remove the tape, but we need to have a closer look at the horizontal force component. If we isolate this horizontal force component generated when we pull with a forward angle, we will see that the tape pulls directly sideways, generating a shearing force that tends to tear skin. This shearing force in no way acts to remove the tape, only to torture tissue. You can try this on yourself. Place a good strong piece of tape on your skin, pull sideways, you're going to feel the shear force. It is not a pleasant sensation, and it's intuitive that sensitive skin should not be subjected to this force. Does our theory hold up? We're going to have a look at a demonstration of tape removal from a metal plate on a tensile tester and see. All right, peel test of 2-inch silk tape on aluminum plate starting now. And we're starting with a straight angle. And we're going to transition to a forward angle now. And then to a reverse angle now. Does our theory hold up? The demonstration graph does appear to validate the theory. Pulling straight up yields this removal force. Moving to a forward angle yields a greatly increased removal force and creates a horizontal component that does nothing to help remove the tape. And yes, pulling with a reverse angle does yield a decreased removal force and creates both horizontal and vertical components that contribute to removing the tape. Does theoretical equal real life? Not always. Skin doesn't always fit the mold. The term theoretical when it comes to skin is a very loose concept, pun intended. We as clinicians know that skin is extremely variable in presentation and characteristics. We know that skin is very different, patient to patient. I'm sure you've all had patients come in and you just know what their skin is going to be like. Likewise, sometimes maybe you're surprised. We know that body location is very different. The brachial plexus is different than the skin at the medial malleolus, or the skin on the scalp, or the skin on the thigh. We know that skin acts differently depending upon humidity, hydration level, core temperature, certainly a myriad of other things. We know that patient age greatly impacts skin characteristics. We know that neonates and geriatrics have very fragile skin. We know that skin tension is dependent on orientation, as depicted by these Langer's lines. In short, we know that skin is complex. The characteristics of skin adhesive removal are best viewed in a real skin demonstration. Okay, this is a peel test of 2-inch silk tape, starting now. And we're going to start with a straight angle. And about to move to a forward angle. And I'm going to move back to a straight angle. And then we're going to go to a reverse angle. So is the theory still holding up? It appears to be. Pulling straight up yields this removal force. Moving to a forward angle yields a greatly increased removal force, as we see. And yes, pulling with a reverse angle yields a decreased removal force here. Okay, so what are some temporary conclusions that we can draw? Skin does not act like this metal. Under the tape removal, the skin flows, it shifts, it adjusts to the forces. Clearly the enemy is shear. Remember, when we're pulling this way, we can just feel that shear on our skin. Well, when we pull straight up, even when we pull back, the skin lifts slightly, right? So we're getting some degree of shearing there. So if there are conclusions that can be drawn at this point, it's that we need to be responsible for owning this situation. Know your patient's skin. Watch as you're removing any electrode. And if you're getting a lot of shear, try to go straight back. Might be weird skin. You can own the process and pull in whatever orientation produces the least shear. So we have considered shear and removal angle, but there is another big consideration: speed. Specifically speed of electrode or adhesive tape removal. So you're hiking a path and notice cars ahead crossing fast from the left and cars crossing slowly from the right. Which are you more worried about? The faster cars, of course. Why? You don't want to be road pizza. What is it about the faster cars that is more scary, aside from being harder to avoid? The faster car would hit you with more energy than the slower car. More energy equals nastier road pizza. The equation for kinetic energy is mass times velocity squared divided by 2. It is especially important to note that the speed or velocity, speed and velocity are the same thing, is squared in this equation. Some demonstrations will help show how important speed is for generating energy. A 3,500 pound car moving at 2 miles an hour would wind up delivering 468 foot-pounds of energy to an object. Increasing speed 4 times to 8 miles an hour winds up delivering 16 times the energy. Increasing speed 16 times to 32 miles an hour results in a whopping 256-fold increase in energy delivered compared to that of the car driving 2 miles an hour. If we graph energy on the y-axis with speed on the x-axis, we get this exponentially increasing curve. In other words, it is apparent that energy delivery is much linked to speed. Every increase in speed yields an exponentially increasing amount of energy delivered. Let's look at another demonstration using hammers and nails.
Let's use hammers to demonstrate the importance of velocity in the energy equation. We have 2 hammers, a 1-pound hammer that you swing and a metal-plated piece of wood that acts as a hammer in this assembly with 195 pounds of out of shape standing on it to drive a nail into this board. Which one's going to work best? Let's use the 1-pound hammer. Worked pretty well. So how does the metal plated board do with 195 pounds on it? Let's see. See if I can carefully balance up here. And there, all my weight is on it. It doesn't appear to be going. Let me try to bounce. And, oh, it's going. It's going. But I'm having to really work at it. Okay, so it's quite evident that the 1-pound hammer did a better job. So which hammer was better? Okay, it's pretty obvious that the 1-pound hammer was just better at driving the nail than this contraption with almost 200 pounds very awkwardly jumping on it. Why? The hammer is at the end of an arc. It's actually moving very fast. It has a high velocity, a high speed. And what this does is it proves that that velocity squared component of that kinetic energy equation is a very important factor. There you go. And next, a look at ballistics will help further prove that point.
These are 2 cartridges that helped win World War II. The 45 ACP is a pistol cartridge used in the Colt 45 pistol, and the 30-06 is a rifle cartridge that pushes a bullet much faster for long-range targets out to a mile away. The 45 typically uses a bullet that weighs 230 grains and moves fairly slowly, in this instance 835 feet per second. The 30-06 can use an almost identical bullet weight. It would push a 220 grain bullet at the much faster speed of 2,500 feet per second. So we know that the 30-06 is 3 times faster than the 45. And when we consider energy, thanks to the velocity being squared in the energy equation, the 30-06 has almost 9 times the energy delivery of the 45. So what does that look like? Using cantaloupes as targets is a great demonstration. We see that speed squared really matters. Hopefully these physics demonstrations have helped illuminate the considerable relationship between speed and energy. The fact that energy exponentially increases with speed warns us to remove sticky stuff from skin. How? Slowly.
I hope this helped. It was fun doing this stuff. And some of these setups were perhaps not the most perfect setup, but are there conclusions that we can draw? I think so. There's four that come to mind. Number one, shear is the enemy. And we can do things such as watching very carefully the direction in which we pull to minimize shear. Number two, our skin is not one size fits all. Patient to patient, day to day, humidity level to different humidity level, even room environment to a different room environment. This can act very differently, as this spot on the back of my hand can be different than this, than the brachial plexus to my noggin. Third, just rip it off, and removing adhesives from your patient's skin do not play well together. Remember that velocity squared component of the energy equation. Every bit you can slow down decreases the amount of energy that goes into tissue. And then finally, we can own the process. We can become better stewards of our patient's skin, and even further decrease lesions from things that we have on the patient. I hope this helped. Please just email me if you have any questions or ideas of other stuff that you would like to see. So good luck. Talk to you soon.